Hello everyone and welcome back to my channel. In this video we are going to talk about visual anomaly detection using convolution neural network. If you are new to the channel, I'd recommend you go back and check the entire playlist where I described about the dataset, the basic idea, and then come and watch this video because it's going to be a continuation. But before starting the video, I think we are going to look at the result, what we are going to achieve from this video. So yeah, I'll let you watch that one. So as you have seen in the video, our goal is to detect if there is any kind of fault in the industrial component. In this case, we are focusing on a rug. So for this particular rug, if you see, so this is the actual photo of the rug where there is the fault here. There is extra color spillage there. And you see our model is able to predict accurately. It is able to to localize the fault pretty accurately. And this is how usually the rug looks like when there is no fault. So in the previous video series, we followed a autoencoder convolution autoencoder method, but there we are giving raw data as input to the neural network, raw image data. And there we see this was our input, this was the reconstruction, and this was the reconstruction loss. So we can see that the autoencoder was not very accurately was able to isolate the fault effectively. So that's why we're coming with a new method. So this new method is highly motivated by this paper, which you can see here, deep feature reconstruction for unsupervised anomaly segmentation. So it does not only does anomaly detection, that whether this image is an anomaly or not, but also segments or localize the anomaly in the picture. So yeah, that's a very good and advanced thing. So that's what we are going to see today. So to start with, the basic idea is we have a lot of normal data in our industrial case, which is present to us in abundance, but there are very few abnormal data, which may look something like this, but the amount of abnormal data we have is very few. So we cannot train a classifier network. Instead, what we do, we train an anomaly detection method. So the model will learn what the normal data looks like, and if there is a data outside of this distribution, then it can detect, okay, this is an anomaly case or abnormal case. This is the paper, and yeah, so it is often used in the industry for the quality inspection. After the thing is produced, then instead of a very labor intensive human job, we can put a camera, and to some extent we can aid the human in doing the inspection task. So what was the knife method that we did in the previous series? So we take the images, we downsample the images into 224 cross 224 size. We put it in an autoencoder and we ask it to reconstruct itself. And it knows all the input data that the autoencoder uses is only normal data. So it only knows how the normal data can be reconstructed. And to detect whether the data belongs to normal case or anomaly case, we just do the difference between the input to the autoencoder and the output. We do the difference by using mean squared error. That is also we call the anomaly score. The smaller the anomaly score is, there is high chance it belongs to normal data. The higher the anomaly score, it belongs to a faulty or not okay data. All right. So let's say we have the normal data here, and this was our older method. But using this older method, we are getting pretty bad accuracy. As if you remember, this was our performance. We are using rectifier receiver operating curve, the area under the receiver operating curve, evaluating the model, and it's not even 50%. It's less than random chance. So it's a very poor model. So in this video, we are going to help this model or we are going to better this model's performance. So in this video, we are going to use the ResNet model. So if you have any idea about computer vision, then you must have heard about ResNet. What we are going to do is we have our images. Instead of feeding this image directly to the to an autoencoder, we'll first extract features from this normal network. And to extract feature, we'll use a pre-trained neural network. In this case, we are going to use a ResNet 50 model, which is pre-trained on ImageNet dataset. Alright, and how do we extract the feature? One way is just extract the feature from the last layer. So just before the classification layer, you have 2048 activation from the average pooling, and that you can use as an input to the neural network. But what I find is this does not work very well, and also it is mentioned in the paper that I'm referring to here. So this idea is cancelled. So what is the other way we can extract feature? We can also extract the intermediate features here. So what we are going to use, we are going to extract the feature from the after the first block and after the second block. After the first block, we have total 512 filters, and each activation map is of size 28 cross 28. And after the second block, we have total 1024 feature maps, and each having 14 cross 14 size. And this is the features we are going to use. But now the problem is, how are we going to use this? They do not even have the same dimension. So in the next step, our goal is to aggregate this feature to have a similar size. So what we do, we get our normal data, and we already using the ResNet, we got features from two different steps, from second after the first layer and after the second layer. Now in the second layer, we are going to upscale it using the adaptive average pooling method to have the same size of height and width compared to the first feature map. And then we are just going to concatenate them, basically concatenate them along the direction of the channel. So finally we have 1536 feature maps, each having 28 cross 28. So now it's interesting. So now it just becomes like an image. In case of image, we have just 3 channels, but in this case we have 1536 channels. Now we can use this extracted feature as an input to another convolution neural network, which will be an autoencoder, and all the process will be exactly same. So let's have a look at how it works. So how to train an autoencoder? So whatever images we have, first we extract the features that we saw in the previous slide using the backbone network. In this case, we are using a ResNet backbone, but you can also use VGG, MobileNet, depends upon your use case. Then we pass this extracted feature into an autoencoder, which is a convolution autoencoder, and the output will also be of the same exact size, and which will be the reconstructed value. Then we obtain the mean squared error between these two. So now we see that when we obtain the mean squared error, it has a 28 cross 28 channel, and that is our fault localization heat map. So here we see that for this particular input where there is a fault, the heat map also accurately identifies, okay, this part has a higher reconstruction error. These pixels are very high reconstruction error. So there is a chance that there might be a fault in this local area. So if we take the mean value of top 10 pixels, we can get the anomaly score for the whole image. So in order to say, okay, whether this image belongs to a normal class or not. And using this particular method, we see that our result becomes significantly better. Before, where we are having ROC curve of 0.42, now it becomes 0.99. And also the predicted labels are also very accurate instead of some misclassification, very few misclassification. Hey everyone, if you enjoy my content and are looking for personalized one-to-one guidance on topics like machine learning, computer vision, pursuing PhD abroad, fault diagnosis or research, don't hesitate to book a call with me from TopMet. Use the link in the description to get an instant 10% discount. Additionally, you can check out my templates for scientific posters, presentation, and international conferences. And in the end, don't forget to like this video and share it on LinkedIn with your connections. So we are going to start with the execution on Jupyter Notebook of the method that we just saw. First, we are going to import the necessary libraries, and then some basic things like defining the transformations that we'd like to do, which is very basic, as resizing the image and then converting into tensor. We'll define the train image path, which is nothing but just here, which is in the training there is a subfolder good, and then there are all the good images where there is no fault. So yeah, then we create the image folder and image folder dataset, which is a Pytorch dataset. If you are confused about this, I will you can click on the I button above to know more about what are Pytorch data loaders and dataset both. I'm defining my batch size and I'm creating two data loader, one for training and one for evaluation or testing. So now comes the most important part of this video, which I think I'll need to explain in a bit more detail. As we are going to use the pre-trained ResNet model to extract feature, first we have to call that or download that. If you haven't already downloaded, it will automatically get downloaded, and it will be dropped in this ResNet model variable, which is basically our network with pre-trained weights. Alright, so now what we need to extract features from intermediate layer. But how do we do that? For that, we have something called Pytorch hooks, which are very useful. So let me show first what are the layers, and then we'll go deeper into the hooks. So these are basically all the layers that we have in this network, but we just need the output from layer 2 and layer 3. So this will be the output from layer 2, and this will be the output from the layer 3. That's it. We just need this to output. So how we can do that? So for that, first I'm going to let it be commented. I can just call resnet.layer2 to see what is in the layer 2. So you see here layer 2 is something like this. Even to be clear, so this is the network we are referring to. So here this output is the layer 2 and this output is the layer 3. So these two output we need. So first we are looking at layer 2. This is the entire block of layer 2, and which can we see here, and we need output from the last layer. So for that, what we have to do, we just do -1 to get whatever is in the end of this second layer, and we see that this is the sequential model we have at the end. We want output from this layer. All right. So how do we do that? So for this, Pytorch offer a very cool and efficient model where we can just call it like register forward hook. So yeah, stay with me. I'm going to explain in a bit how this extracts the feature from this particular layer. So using this register forward hook, the model knows that in this number of layer at this position, I need to give the output. I need to provide an output. And how does it know this? By using this hook. So what is this hook? So the hook is just a defined function, and you have to define the function in this way only. So you have the model, the input and the output, and what we call, and this in this hook function, we say that append the output of the attached layer to this particular list feature. So we have to also initialize this feature list, otherwise we'll get an error that because whenever we'll call this model, it will call this hook, and if we haven't defined the feature list, it will give us an error. So we have to define an empty list. Then we just do the forward method, or we just do the prediction, and the output from this particular layer will automatically get appended to this empty list. We attached our hook, we defined our hook. Now we just have to do a forward pass. So I'm doing a forward pass on a random images to see that what is the output we are getting. So right, and I'm not saving the output. The output, I don't need the output, which is basically the 1000 class labels. I don't care about them. I just need the intermediate layer, but we didn't get anything. So here, if we check on the feature 0, because this is the first list, and if I do shape, see here I got the output from the second layer. If we pass this image, this will be the output. This will be the output shape from the second layer. And if I want to, because I also need from the third layer, the output from the third layer, then I can just do like this, and instead of layer 2, I just put layer 3. Now I again do the forward pass, and this was for the first feature, and if I do the second feature, then see I get 1024 14 cross 14. So like this, with very easily I get the activation from the second and the third layer. So instead of doing this method every time I do an inference or the feature extraction, I put them in this ResNet feature extractor class, which is inherited from the nn.module, and there it's very simple. First, what I do, I get the ResNet model with pre-trained weight. Then I keep all the parameter frozen, that I don't need any training, so you stay frozen. Alright, then I define the hook that I just did before, and I attach the hook in my layer 2, in the end of layer 2 and end of layer 3. Then when I do the forward pass in the feature, I get accumulated, the features are accumulated, and then the aggregation function happens. So what is the aggregation function? To remind you, this was our aggregation function, where we from the downscaled part, we upscale it to match the dimension of the other feature, and then we just concatenate them. That is what happening here. But one extra thing is I'm also doing an average pooling to smooth out the feature. So I'm one average pooling, and then adaptive average pooling to match the size, to make both the feature have the same size of height and width. This patch is basically the concatenation of both the feature, where both have same width and height. And in the next step, I'm going to show how can we use this. We created this class, and now I'm going to create an instance of this class, and we are going to use that for extracting the feature directly. So first I open the image, then I transform the image and add an extra batch dimension using unsqueeze. Then I pass it, then I instantiate the ResNet feature extractor class that I just created, and this is the instance of that class, which I call backbone. And I just pass this image, which is a tensor, through this backbone to get the features. Alright, and if you see the feature.shape, the feature.shape looks something like this: 1, 5, 3, 6, 28, 28. So I have total 1, 5, 3, 6 channels and 28 height, 28 width. Okay, and if I do the plotting, I show the image, and this is the image that I'm using. So next we are going to look at, we're going to visualize what are these features. So what I did, out of this 1, 5, 3, 6 channel, I randomly selected I think 10 channels, and I plotted them, that how do they look. Each of them is a 28 cross 28 sample, and we can clearly see that some of them, like here exactly, it automatically detects there is an error in there. So for this image, it automatically detects this. Here also you can see. So majority of the case, this already extract a pretty meaningful features. All right. And in the next step, it's very similar to the last video series, where we just define our autoencoder model. First, this is going to squeeze the higher dimension to lower dimension, then from lower dimension to higher dimension. Is nothing special. We have the encoder part, we have the decoder part. That's it. And then X is the final prediction. we have to define the in channel of the model. This feature CA is this model, which is CA, and this entire model architecture is taken from the paper that I showed at the initial part of this video. All right, and it is just an autoencoder model, nothing special there. I'm using mean squared error loss and an Adam optimizer with a learning rate of 0.01. Then because I already trained this model, I'm loading from this checkpoint. If you do not know how to load the model, then please look at my previous videos where I have exactly dedicated, I dedicated entire video on defining how you can load a model, how can you save a model, how you can train a model, etc. in Pytorch. Okay, so this is our entire training loop. If you look at this training loop, nothing special, exactly same as before, but there is two more things. So what we are doing, we are also iterating through our data, our training data. Then we are passing our training data from the backbone to extract the features. And then we are putting this feature in the model, the autoencoder model, to get the reconstruction. And then our loss to train this model is between output and the feature. So the better our model is able to reconstruct the input, the lesser is the loss. And same for the evaluation loss, nothing, just to track it. Then you train it for several epochs, and then we can save the model for future use. So after the model is trained, now it's time for doing some inferences. First we open the model, we convert it into a tensor, we pass it through our backbone model to get the feature, and then pass the feature through the model to get the reconstruction. And what is our reconstruction error? It will be the difference between the feature and the prediction. So feature minus reconstruction, we are doing mean squared error, that's why there is a square term. And then I'm taking the mean of this, because we have 1536 channel, I'm just taking the mean across the channel. So now we have just 28 cross 28 matrix, and we can plot them like this, showing the heat map. So this one, this first image, you see it's the test color. So this is the actual image, and this is the generated heat map. And we see that it's way better than the previous use case where we're using the autoencoder. It's way better than that. And then this is the, and then there is this decision function I am using. So what it does, first we get this segmentation map, which is basically a 28 cross 28 map, but we want to get a single value for this entire image. How do you do that? One thing is you can take the mean of all this value, and we can signify, okay, that is my whatever is the mean, that is my anomaly score. If the higher is the reconstruction loss, and then higher will be this mean, that means there's more chance it belongs to a not okay or abnormal case. But in this case, I'm not taking the mean, because mean can be highly sensitive to outliers. In this case, I'm taking top values, top k values. In this case, I'm taking top 10 values, and I'm taking the sum of them, because the higher the reconstruction loss, there is higher chance it belongs to a not okay case, right? So that's why I'm just taking the highest values, and the mean of them, I'm giving it a highest 10 values, and I'm just assigning that as my anomaly score. So this is this decision function. So now I will iterate through all the training data of the good case, of the normal case, to see what is the approximate value of anomaly score I have on the normal data, so that I can get an idea that above what value I can say it as an anomaly. So for that, I'm just iterating through my normal data, and then I'm passing the segmentation map through this decision function, and I'm defining it as an anomaly score. One thing to note here is, what is this? This is because when we do the convolution in the autoencoder, during the transposed convolution, when it comes from the latent space to the actual space, there we use transposed convolution, and there during the edges, it cannot reconstruct very well. So in the edges, you always get very high error. That's why I'm using this. I'm just neglecting. I'm not taking the edges, the value from the edges. I'm just taking the center part. So that's one change what I did. And if you see here, I plotted the value of anomaly score for the normal data, and we see that most of the data lie towards the left hand side of this red line, that most of the data is less than 0.02 anomaly score. Then I did it on the not okay case. That means, what is the not okay case in my, and after I iterate through all the not okay or test data where there is both okay and not okay case, I get the histogram something like this. We saw that our normal, for the normal case, it's most of them are less than 0.02, but here most of them are greater than 0.2, except for some which may be belonging to this good sample, because in the test data we also have good sample. So to evaluate that, I'm obtaining the ROC curve. So for the ROC curve, I'm using this y true and y prediction to value, and I'm passing it through this ROC UC score to get the exact score. So what is the score I'm getting? I'm getting the score of 0.98, 0.98, 0.99. All right, and if I use the threshold, I'm getting an pretty good confusion matrix. We see most of them are well classified, but there are 4 misclassification. And this is the particular animation you saw at the start of the this particular video. That okay, so you see there is a fault here. Then this is the anomaly map generated from this method, and this is the segmentation map. Okay, in this particular region, there is high chances that it belongs to, in this particular pixels, is high chances that the fault lies. All right, so yeah, so that was all about this video.